sort of just a couple of administrative topics I wanted to mention. So we have all your lab reports. We're going to try to get these back to you before your Lab 2 report is due. I don't promise we'll be able to do that just because we pushed back the deadline for the Lab 1 report, so it gives us less time to grade it. And they take quite a bit of time to grade, so I'm not entirely sure we'll be able to get them back to you by then. However, in any case, I wanted to, I've read through the reports. We haven't gone through and assigned grades, but I've read through all of them, and I just had a couple of impressions that I wanted to go over as you will start to work on your Lab 2 reports. The first one is, and this is largely in connection to the hardware section of the report, which I understand is a weird section this semester. So it's not surprising to me that these were sort of all over the place. So I wanted to just talk about that for a minute or so. Generally speaking, your lab reports should largely stand on their own. So in a lot of the reports I saw in the hardware sections, things like see the hardware webpage. What I would ask for you to do instead is to, we have a bunch of infrastructure, a bunch of hardware infrastructure set up for you to use in various labs throughout the semester. If in future lab reports, you could instead pull up the schematics and indicate the parts of the schematics that you're actually using in that particular lab, that would be great. And the reason for that is, there are really two reasons for that. The first is, as I talked about in lecture 1 or 2, is this class is about hardware software co-design. So your software that you wrote is intimately depends on that schematic. And it would be good to go look at that schematic and understand those connections. So for example, if you're talking about the section of your software where you set up the SPI connections to the DAC, and you're doing a peripheral pin select mapping to certain GPIO ports, provide the schematic and say, and this is why we're doing these ports, because as you can see in the schematic, we've hooked up the DAC MOSI line is hooked up to RPB whatever, pin RPB whatever. So please just attempt to make that connection. The other reason for that is, the other big point of this class that I talked about is attempting to provide you all with extremely sort of immediately practical skills, and reading through other people's schematics and understanding them is something that you will do forever. For your entire life as an electrical engineer, you'll be doing a lot of reading through other people's schematics and understanding it. So for that reason too, I'd ask for you to just include part of the schematic and indicate the parts that you're using. What I'm going to do in today's lecture is go over, we sort of introduced Lab 3 on Friday. And today I want to get into more of the technical details of Lab 3, largely through walking through the webpage. And then I'm going to spend some time looking at the code for setting up the analog to digital converter on the PIC32. The ADC has a bit more configuration than some of the other hardware peripherals, so we'll talk through some of those configurations. What I'd like to do on Wednesday, if people will find this helpful, is I'd like to devote Wednesday to a group discussion about final projects. And we'll spend the whole time kicking around various ideas so that we can get a better understanding of what is reasonable and unreasonable given the constraints of this semester. So in anticipation of that, if in the meantime, you folks could, if you have an idea or a few ideas for final projects, if you could just jot them down on a piece of paper to bring up in lecture, that would be very helpful. Or if you just have an idea for a category of things, I'm vaguely interested in music, or I'm vaguely interested in wildlife or computer graphics or video games. Just write down categories of stuff you find interesting, and we can kick around ideas within those categories. And I'm going to do the same thing so that we can start discussing the sorts of things that would make sense in a remote learning version of this class. Will people find that helpful? I don't want to waste people's time, but I do, just based on conversations I'm having in lab, I get the sense that something like that might be nice at this point in the semester. And the reason it's nice at this point in the semester is I'm going to ask for you to turn in your final project proposals, I think probably on the same day as your Lab 3 report. So that would be a week into lab 4, which is a week before lab 4 ends. I think that's when we'll do it, maybe even slightly earlier, just so that we have time to read through them and give you feedback before the end of lab 4 and the start of the final project part of the course. So it seems like a good idea to kick around a few ideas. And many of you already have ideas, but some of you are still trying to figure this out. So hopefully that'll help. Any questions from anyone? Questions about course logistics? Any pending questions about Boids? Okay. I've been wandering through 238 and I see a lot of Boids on TFT displays, so things seem okay. I see some big flocks of Boids too. Okay, if there are no other questions, and if anything occurs to you, just interrupt me, then I'll get into the content for today. I'll just share my screen. And I want to essentially walk as a group through the lab 3 write-up. So as you will recall from last time, the objective for lab 3 is to build a real-time audio spectrogram where the user interface degree of freedom for this lab is changing the range of the spectrogram. So there's some mathematical considerations to think about with this particular project, more so than in some of the other projects. So I want to take some time to walk through some of these things. The first mathematical topic that I want to remind people of, because I think all of you will have seen this at some point now, is the Nyquist sampling theorem. This is familiar to people, right? Some signals class or something. In any case, the Nyquist sampling theorem it tells you how to go from, it tells you the limitations associated with going just with discretely sampling a continuous process. So if you have some continuous process like sound is a fundamentally continuous thing, and you're discretely sampling that thing, what the Nyquist sampling theorem tells you, in approximate wording, what it tells you is how quickly do I need to sample that continuous process in order to reconstruct increasingly high frequency aspects of that process. So if I'm speaking or say I'm listening to some sound that has components up to 5 kilohertz, how quickly do I need to discretely sample that sound in order to recover the highest frequency elements of that sound? And what the Nyquist sampling theorem tells us is the speed with which you need to sample that signal is at least twice as fast as the fastest element of that signal. So in the case of sound, say the sound that you're listening to contains elements up to 5 kilohertz. What the Nyquist sampling theorem tells you is you need to sample that sound at least 10 kilohertz. So what are the implications of this as far as lab 3 goes? Well, what that means is when you move that slider, you're going to be changing the effective range of the spectrogram. So you're going to be doing your analog to digital converter sampling within an interrupt service routine, because just like when you were producing sound, when we're listening to sound in this case, precise timing is important. So in order to get that timing, we're going to set up a timer and a timer interrupt, and we're going to get our analog to digital converter samples within that timer interrupt. So the question is, how frequently does that timer interrupt need to fire for the range of sounds that you're interested in representing on your spectrogram? And the answer is it needs to fire twice as fast as the highest frequency that you want to recover. So when you slide that slider, what's going to happen in your code is you will have to disable interrupts, turn off the timer, reconfigure the timer to a new overflow value that is at whatever value is necessary to interrupt at the speed that is necessary to make that range adjustment, and then re-enable interrupts. So there's going to be a few more steps involved with a slider movement in this lab than there were in previous labs. We'll get into the details of this, okay? But but you need to be cognizant of these sorts of things. Changing the range of the spectrogram is slightly more involved than, say, changing a parameter value for voids. It's just a little more footwork involved in doing that. But okay. You will have some interrupt service routine that's running at some rate, whatever rate is required in order to recover signals that are as high frequency as the range of, as the user input range of your spectrogram. Within that interrupt service routine, you'll gather some amount of samples. In fact, you're going to gather 512 samples. We'll talk in a moment about why that length makes sense, but you'll gather 512 samples from the analog to digital converter. And you will pass that array of samples to an FFT function. What the FFT function is going to do is decompose, or not decompose, but it's going to transform that time domain signal into a frequency domain signal. It's going to compute the FFT of the samples that you sent it. For this lab, we have provided you with a function that will do this. We've provided you with an FFT function. The reason for this is we wouldn't have necessarily had to do this. This is perhaps a merciful thing for us to do. But the reason to do this is we want to keep you focused on the elements of this project that this class is really about. And the algorithmic development of the FFT, while that's really cool and interesting, it's not quite what this class is really about. This isn't really an algorithms class. It's more about the implementation of stuff on a microcontroller platform. So in order to keep you working on those sorts of things, we've provided you with the algorithm, a function that will compute this algorithm, and you have to implement it. So that's why we're doing this. But we can talk through the inputs and outputs of this FFT function that you'll use. There are the version that's represented here takes as input two array, well, it takes three inputs. Two of those inputs are arrays of type accum, and these are the real and the imaginary parts of the time domain input to the FFT function. Now, in our case, we're sampling sound, so we have purely real inputs. So you will always have, for your imaginary input to this function, an array of zeros. And as your real input to this function, you will have your array of audio samples. That array, as I mentioned, and for reasons that will become clear, will be an array 512 elements long. So you'll interrupt 512 times, accumulate a bunch of samples. You'll window those samples, which is something I'll talk about in a moment, but you'll accumulate 512 samples, store it in some array, and then you'll pass that array to this FFT function along with an array of zeros that is the same length. And that array of zeros represents the imaginary part of the signal, which is zero in the case of real valued sound. The last argument to this function is the length of the array that you have passed as a power of 2. So if this array is 512 elements long, then m here is 9, because 2 to the 9 is 512. If it was 256 elements long, it would be 8, because 2 to the 8 is 256. So you'll pass your array of audio samples here, your windowed audio samples, an array of zeros of the same length, and in your case, 9, because 2 to the 9 is 512. What this function then does is compute the FFT. And if people want to have an extended discussion about how FFTs work, I'd be happy to do that. I'm not going to do that today. I want to focus more on Lab 3 specific stuff, but if people wanted to talk about that, I'd be happy to. This computes the FFT, and it stores the output of the FFT. The output of the FFT will have both real and imaginary parts, and it stores them in the same arrays that you passed to it, in the case of this particular function. So it stores the real part of the output of the FFT in the array named FR in this case, and it stores the imaginary output of the FFT in this other array. What you will then do in your code, well, actually, let me take a moment and talk about something else first. Before you pass this array of samples to the FFT, you need to window those samples. And there are many different options for how to window your samples. But generally speaking, what this is for is The FFT algorithm assumes that the signal that you've sent it is periodic over the sampling window. So it assumes that you've passed it a function that repeats over the sampling window, which means that we need to sort of enforce that, because the signal that we send the FFT is not necessarily, and in fact, generally speaking, is not periodic over the sampling window. A way to make it periodic over the sampling window is to attenuate the two sides of it to 0. This makes sense. So if it starts at 0 and it ends at 0, then it's periodic over the sampling window. Now, so we're essentially applying a windowing function. Much like you did in lab 1, you applied a linear envelope to your bird sound, right? In this, we're doing something very similar in this case, where we're applying a windowing function that zeroes the samples at the edges and maintains their amplitudes in the middle. Now, in this case, we benefit from making the windowing function smooth. So there are many different options of window functions. The one that I'm going to recommend for this lab is a so-called Hahn window, which is essentially the top part of a cosine curve. Looks like this, okay? So if we have some raw audio sample that, you know, contains a bunch of sine waves of a bunch of different frequencies, sort of additively combined, linearly combined, we apply this windowing function to it. You end up with something that looks approximately like this, right? The same signal, but attenuated out at the sides and attenuated smoothly. If we weren't to do this, if we were just to pass the raw audio samples into FFT, what we would end up seeing is a lot of high frequency stuff in our FFT output. For reasons that were very similar to when in lab 1 you did not linearly envelope your bird calls, you heard a bunch of high frequency stuff at the output, clicks and pops and such, right? That sort of thing will manifest in the FFT output as well. So by windowing this, we get rid of all of that high frequency, just noise. It's not signal, it's just noise. Okay, so we have an ISR gathering 512 samples, windowing those samples with a Hahn window, and passing them to this FFT function. This FFT function is storing the real and imaginary outputs of the FFT in those two arrays that we've passed in. It's storing them in place. What you will then do to compute the spectrogram is you will go through these, you will compute, so the output of the FFT is a complex number, real and imaginary parts. And the real part of the complex number is stored in the real array. The complex part is stored in the complex array. What you're representing on the spectrogram is a magnitude. So you will loop through the two output arrays of the FFT and compute the magnitude of each complex number represented in that array. And you'll do so using the same algorithm that many of you are using for computing root sum of squares in the Boyd's lab, which is the alpha max beta min algorithm. So you'll start at index 0 in both arrays. Index 0 of the real array represents the real part of the first output, so to speak, of the FFT, and index 0 is the imaginary part of that same complex number. So you'll use the alpha max beta min algorithm to compute the magnitude of all of these complex numbers. And then you will use those magnitudes to colorize a column of pixels according to those magnitudes. Once you've done that, you will move on to the next row of pixels and you'll repeat this whole process again. You'll gather 512 more audio samples, apply the window, pass it to the FFT function. The FFT function will return the real and imaginary outputs of the FFT of those samples. You'll compute the magnitudes of those complex outputs and plot a new column of pixels colorized according to magnitude. And then you'll go on to the next one. And you'll end up building across the screen a time history of the frequency content of the input. When you get to the end of the screen, you'll go back to the beginning of the screen and start drawing over what you've already drawn, much like an oscilloscope does. And you'll be asked also to erase a little bit in front of the line that you're drawing. It just makes it easier to look at. You'll see that oscilloscopes do this too, right? So You'll draw across the screen. When you get to the end, you go back to the beginning and start redrawing, erasing a little strip in front of where you're redrawing. Questions about this? Why 512 samples? Why does that make sense? Well, it turns out that for purely real inputs to the FFT, the output of the FFT is mirrored across the n/2 sample. So if the output of the FFT is 512 samples long, for purely real input, that output is mirrored across sample number 256. 256 is kind of close to the height of the TFT screen, which is 240. Right? So it's a number that just kind of makes sense for the amount of pixels that we have available. And then the question is, so a question to ask is, what range of frequencies is represented in each pixel of your spectrogram? And the answer to this is going to be, it's the Nyquist maximum frequency for your sample rate. So say you're sampling at 10 kilohertz, then the maximum frequency that you can resolve is 5 kilohertz. So it's going to be 5 kilohertz divided by the length of the array, which in your case is going to be 512. So you can do the math, and the amount of frequency that's contained within each of those pixels will change with your range setting. But you will need to do this math in Lab 3 because you are asked to draw the axis for your spectrogram labeled with the appropriate number of hertz as you move up the y-axis. So 0 is always going to be at the bottom. At the top, you'll have something a little bit less than the Nyquist maximum. And then in the middle, those values are going to change as you slide the slider.
I have a question.
Mm-hmm.
So when we use the window, we're basically attenuating samples towards the edges of the window. So in our FFT, won't this misrepresent the amplitude of those signals in the actual signal? What I mean is we're attenuating certain samples of the signal. So won't their amplitude be misrepresented in the spectrogram?
Everything is a compromise, and you're trading off losing some information at the edges with attenuating high frequency artifact. How could you fix this easily? The answer is 50% overlap in the samples. So you oversample so that you can always get full data. We're not asking you to do that because what Hunter hasn't said is that there's an assumption that the signal is stationary over the window. You know what stationary means, statistically stationary?
Yeah, it means the signal is periodic and it's sort of constant for a certain amount of time.
Right. So for your voice, over what period can you assume it's stationary?
I guess a couple of milliseconds at least.
That's actually, since the fundamental of your voice is about 100 hertz, I would say 10 milliseconds minimum. All right, so the question, I mean, this is something you have to think about all the time when you do FFTs.
Right. Also, one other thing, why specifically the Hahn window? Is there a reason we chose that? Could we have chosen something like a Gaussian window or something like that?
You certainly could have. And if you go to, as with a lot of this stuff, the Wikipedia page associated with these window functions is excellent. So if you go to the Wikipedia page associated with these various windowing options, what makes each option different from the other options is what its contribution to the frequency output is. So you can look at, for the same signal with different windowing functions applied, the output in the frequency domain looks different for each one. And for certain applications, one might be more attractive than the other one. Why did I choose the Hahn window in this case? I could have chosen another one. You can certainly do another one if you want. This is not sort of a strict requirement of the lab. This is a suggestion that makes the spectrogram looks nice. There are other windowing functions that would also make the spectrogram look nice. You can experiment with those. But the shorter answer is, it's a good option. Its output in the frequency domain sort of looks nice for this application, and that's the reason that I chose it.
Okay, thank you.
Yeah. It also has the benefit of being relatively easy to implement. So the way that you'll actually end up implementing this is much like in lab 1, you ended up storing a sign table. In main, you computed a sign table and you stored it in some array, and then you use that sign table later on in your actual real-time application. In this case, you will also compute and store your windowing function so that when you're gathering data from the ADC, you can just index into your window function array and apply the window function as you gather samples, right? So you're keeping track as you gather of, I'm gathering sample number 100 now of 512 in this array. So I'm going to window it with whatever is stored in index 100 of my window array. And then when I gather sample 101, I'll store it with whatever is stored in index 101 of my windowing array. Other questions?
I have a question.
Mm-hmm.
In the function that's computing the FFT, the output is also 512 elements long, right?
Yes.
So what physical value is actually stored in those arrays?
What physical value is stored in the output of the FFT?
Yep.
Oh boy, is that a conceptual question. Bruce, do you have a good answer for that?
Well, let me try one. So in each element of the array consists of the phase locked frequency component. So in the real part is the cosine component of a given frequency band. In the imaginary part is the sine component. Once you get up to the Nyquist frequency, once you get up to n over 2, then you have a reflected version of all of the frequency components in the higher bins, and the reason for that is there's no imaginary component for this signal.
Okay.
Does that answer what am I answering what you're asking?
I don't know actually, because I was looking at the code for the FFT, and what's basically happening is as per my understanding, we are converting a 2D plot into a kind of 3D plot, because in the time domain, when we are inputting the signal, it's basically time versus amplitude, right?
Yes.
Mm-hmm.
And when we are converting that using FFT, then on one axis it's time, on the other it's frequency, and on another axis there is amplitude as well.
Sure. Well, the bins in the array are the amplitudes.
Right. So that's what I'm actually trying to understand, because even the output of the arrays is actually, I guess, 2D, if we can say, because on one axis there's the index of 512 index elements, and on the other axis is the value that will be stored. And so how will we compute the third
So,
axis? That's what I'm trying to understand.
so keep in mind, the input to the FFT is the real part of the signal and the imaginary part of the signal. And the output of the FFT has both a real and imaginary component to it. So you're putting two arrays in and you're getting two arrays out, and both of those arrays are the same length.
So let me try this. You're expanding the one-dimensional input signal into 2 dimensions so you can more easily understand it. And the way you're expanding it is you're applying a Fourier transform to it along a vertical axis, and then clumping time together into windows along the x-axis. So, and then what's plotted at each point is the output of the FFT at that frequency, which is an amplitude.
Right.
Now, what's missing in your brain or in the explanation?
To be honest, I don't know. I was just going through the code briefly, and I'm trying to actually understand it on the programming level, not the mathematical level. So I guess I'll figure it out once I take a good look at it.
Remember that an FFT has already been highly massaged was invented in 1964 by two researchers, Cooley and Tukey. And what they did was they took the straightforward discrete Fourier transform, which is an average at each frequency. It's a cross correlation between each different frequency and the input signal, and they mathematically massaged it for efficiency, but that does not make it clearer. It is a DFT, a simple DFT that's been rearranged to be optimized.
Right.
Something else that can sometimes cause confusion is my experience is that it can sometimes cause confusion that you feel like you are putting in real values like amplitudes, sampled sounds, and you're getting out a 2D something, getting out 2 arrays. And the thing to remember is we're doing this thing that is often, a trick that is often pulled, which is we're representing a real number as a complex number with 0 imaginary part. So we are inputting 2D numbers, complex numbers. Those complex numbers just have 0 imaginary part, and then we're getting out complex numbers. And the output does not necessarily have 0 imaginary part. It has both real and imaginary components. And we can compute the magnitude of those complex numbers.
Right. Okay.
Other questions about this? This is one of those things that there are levels of abstraction to this particular concept, and you can approach it from a few different levels. There's a deeply mathematical way to think about this, and then there's a coding way to think about this, and then there's an implementation way to think about this. And it's interesting to talk about all of those aspects of it. In this class, we're asking you to focus specifically on implementation, understanding the FFT largely as an input-output system. If you want to talk about those other levels of abstraction, like I said, I'd be very happy to. But I'm just reassuring you in the event that you're going, Jesus, like what is going on? I'm reassuring you that in this class and for this lab, the FFT is an input-output. You put stuff in, you get stuff out, and you do stuff with the output. And that's how we're treating it in this course. If you want to talk more deeply, I'd be happy to, but just a little bit of reassurance.
By the way, if you really want to understand an FFT, make yourself a program where you can draw an input and look at the output, then draw another input, look at the output, and do that for about 2 days. And then you'll have an intuition for how FFT works. Everything's a time commitment.
Any other thoughts before I move on with just a few other things? Okay. I want to go over just a couple more things in this document before. I don't know if we'll have time to do the ADC configuration today. We might save that for Wednesday. In any case, there's some external hardware associated with this lab that is set up for you, but I want to go over what it is so that you know what you're using. The first piece of external hardware is there is a passive circuit. There is a passive circuit that sits between the headphone jack output of the lab PC, where sound will be coming from the lab PC, and the analog to digital converter input of the PIC32. And the circuit that sits between these things is the one that's pictured here, which is a biased high-pass filter. This circuit solves a problem for us. The problem being that the output from the headphone jack of the lab PC is going to be a voltage that's in the range of -2 to 2 volts. And the analog to digital converter of the PIC32 requires a voltage that is in the range of 0 to 3.3 volts. So we need to do some adjustment, and that is what this biased high-pass filter does. So this is a biased high-pass filter because it's essentially a combination of two things, one being a passive high-pass filter and the other being a voltage divider. So if you look at this aspect of the circuit here, this is a very simple voltage divider where each resistor here is 10K volts, which means assuming a DC current here that's getting blocked by this capacitor, or assuming that this part of the circuit doesn't even exist, then the voltage that we would have right here is 3.3 over 2 or 1.65 volts. So we've biased the voltage at this point up by 1.65 volts. And then we're passing in the output of the headphone jack of the lab PC through this high pass filter. You all from some circuits class remember what the equation for the cutoff frequency of a high pass filter is. I'll remind you it's 1 over 2 pi RC. So if you were to compute 1 over 2 pi RC for this particular high pass filter with a 1 microfarad capacitor and a 10K resistor, we have a cutoff frequency of something like 16 hertz. So this is going to attenuate out signals beneath 16 hertz and it will pass signals above 16 hertz. Why is that a cutoff frequency that makes some sense for the lab that we're doing? You can't really hear stuff beneath 16 hertz. So if you can't hear it, it's an appropriate place to do a cutoff, right? So it's going to cut off DC stuff, and it's going to cut off all signals below 16 hertz, and it'll pass the other ones and bias them up by 1.65. Now, at full volume, this is a ±2 volts. This is going to bias it by 1.65 volts. So if you have your output of the lab PC at full volume, it is possible that you will see some clipping in your analog to digital converter samples. The solution to this is to turn down the volume a little bit so that the input voltage is not between ±2 volts, but instead turn the amplitude down to ±1.65 volts or lower, and then you'll be comfortably within the range of 0 to 3.3 volts for the analog to digital converter. Does that make sense?
How would you tell by looking at the spectrum output that your signal was clipping at the input? Anybody?
I guess discontinuities in the graph.
Well, remember, you're only looking at the spectrum.
Now, if there's clipping, you're going to have a lot more high frequency energy because the waves look more square.
Exactly. And so you're going to get the spectrum of a square wave out. If you put a sine wave in, you'll get a spectrum of a square wave out. That tells you it's clipping. Thank you.
And by the way, if you see nothing on the output, make sure that you don't have your PC muted. And I only say that because that's a bug that took me like maybe an hour to solve, and I was like, oh, I just don't have the volume on. Okay, so just keep an eye out for that sort of thing as well.
Hunter, are you going to have the oscilloscope probe hooked up to the output
Yes, I
of the
am.
low pass
Yeah.
filter?
So that's the next thing I was going to bring up is for this lab, your scope probes have been in the same place in your circuit for the first two labs. They've both been on the DAC outputs for labs 1 and 2. For lab 3, I will move scope probe A or scope probe 1 to the analog input pin, so that you can actually, like in the last lecture, we were looking at my voice in the time domain and stuff like that. You'll be able to see the actual input to the analog to digital converter so that you can keep an eye on those voltages. Now, I don't want to move your scope probes until I get the okay from you, because it's possible that you're using those scope probes to gather things for your lab report. So in the spreadsheet that we use to keep ourselves organized during lab sections, when you're ready for the scope probe to be moved, I'll ask you to indicate it in that spreadsheet, and then we'll go move your scope probe, and you'll be able to see the analog input to your PIC32. Okay. Okay. So I'll talk briefly about the recommended program organization. As with all the labs, this is a recommendation, and it's not even a strong recommendation. Okay, there are plenty of other good ways to set up a program, and if setting it up in some other way makes more sense to you, that's fine. I include sections like this so that if you're in a position of thinking, oh my God, I don't even know how to start, I'm trying to get you over that initial hurdle. So if you want to set things up differently, that's totally fine. But here's a suggestion. You might consider setting this up such that you have one interrupt service routine that it would be configured with a timer interrupt. So you have some timer configured to overflow after a certain number of cycles. How often that overflows depends on the desired range of your spectrogram. Right? The speed with which you sample is connected with the maximum frequency that you can resolve on the spectrogram. So that will change as you move the slider. But in any case, you'll have some timer configured to interrupt. And when you interrupt in that timer, you will gather an audio sample from the analog to digital converter. You'll scale that sample with the Hahn windowing function. And you'll do that 512 times, storing 512 audio samples. And then once that array is full, you will have some logic in your interrupt service routine that stops affecting that array until it is told by a thread to continue to fill the array. And it will signal to your program that the array is full. In your program, you'll have a couple of threads. Okay, so as usual, you'll have main doing the stuff that main usually does, which is opening a timer, configuring the interrupt. You'll be affecting that interrupt in your threads in this particular lab, but you'll open and configure it initially. Open and configure the analog to digital converter, initialize the TFT, create your Hahn windowing function, set up the proto threads and schedule them and such. In your spectrogram thread, or whatever you want to call it, this thread will wait until it gets a signal from the interrupt service routine that that array of samples is full and ready to have math done on it. Okay, so it will wait until it has a full array of samples. It will then disable the interrupt, copy the samples into some secondary array, do it through a mem copy probably. Signal the ISR to start refilling the sample array while you're processing the previous array of samples, and then pass that array of samples to the FFT function. So it sits and waits for that array of samples to be full. When it gets the signal from the interrupt service routine that there's a full array of samples, it copies it into a local array, signals to the ISR to start filling up that old array again so that you're not wasting time, and then passes the array of samples to the FFT. The FFT will do the FFT on that array of samples, and the output will be two arrays, the real and the imaginary components of the output of the FFT. You'll compute the magnitude of those complex outputs, and you'll plot them on your spectrogram. And then of course, you'll have your Python serial thread that is interacting with your user interface. In the case of this lab, it will be waiting for slider input, which represents the desired maximum frequency. And in the case that the slider moves, it will disable the interrupt timer, redraw the axes for the spectrogram, open the interrupt timer at whatever rate is required to get to the desired user input frequency, maximum frequency, and then reopen the interrupt timer. You might set this up differently. This is a suggestion. How might you set this up differently? Well, if you were so inclined, you could, instead of sampling the ADC in an interrupt service routine, you could use DMA to do that if you really wanted to. And there are some examples on the course website of how to do that. You don't have to do that, but if you want to do that, you could do that. Questions about this? I'm not gonna get into the ADC configuration code today because we're out of time, but what I will do so that folks are looking at the right place as they get started on this is on the analog to digital converter webpage. There's some examples here showing how to set up the ADC and how to read the ADC. This is the place to go look to start. And even this setup code sets up the analog to digital converter AN11, which is actually the one that you'll be using for this lab. So this setup code should work precisely as specified in lab 3, and in, well, maybe Wednesday, in one of the coming lectures, we'll go over these configurations in detail. If in the meantime you want to open up the reference manual and read about this, obviously do that. But in the meantime, this is the place to go to look for where to start with the analog to digital converter and for a bunch of other information about it. Okay. Questions? Okay. In that case, I'll see some of you in a little over an hour, and I'll see the rest of you Wednesday, if not before.